Okay, so if you haven't come get your exam, so on the back of the front page is where everything is graded. So in red is sort of the original score, which is like how many points you actually got on the questions. And then most of you will see that there's quite a significant curve. Um, the raw average was like a 45 or something, and that's not actually much worse than I expected. So don't feel too bad. And then I curved it to bring the average up to roughly a 70 or something like that. So I think right now the average in the course, so including the homework scores, is like a 75 or something like that. Of course, if you got a really good grade, you got less of a curve because I sort of took all the scores and kind of crunched them up a little bit. But any questions on specific questions? This chapter we have more time than we really need, so we have a little bit of time. Any particular problem confusing? Also, I should mention I just posted the answers to this is Buford, but same thing. There's now an exams folder and a blank exam, so if in case you want to redo it and practice for the final, and then the answer key because everybody has taken it now. Let's see. The chair structure, there's more structures here that are correct. Yeah. Cool. Any questions? All right. You're welcome to come to office hours, of course, if you like to chat about that sort of thing. Okay. So next topic is this chapter is really a hodgepodge of a bunch of different things. Mostly, you're going to talk about resonance structures and a couple other things as well. So, molecule of the day for today is benzene. This is a good molecule of the day for one of the lectures in organic too, but I figured what the heck, we'll do it today. So, there's the structure of benzene. It's a hexagon with alternating single and double bonds. So, this is not a cyclohexane. It's its own sort of unique thing. Turns out benzene has some unique properties, and again, we'll talk about that in organic too. But essentially boils down to the fact that it's an aromatic compound, and the word aromatic comes from the lay term aromatic, as in like smelly in a good way. Don't really think benzene smells that good, but a lot of aromatic compounds that have this core structure of the six-membered ring with three double bonds. Many of them have nice smells. Anyway, it's a component of gasoline, fortunately, in pretty small quantities, about 0.5%. I think the legal maximum is 0.62 or something like that. It used to be a much more significant contributor, but the problem is it gives you cancer. It's carcinogenic. And it also used to be a really, really popular lab solvent. It's extremely nonpolar, so like hexane or something like that. And so it's really good at dissolving nonpolar substances. It's also good at giving you cancer. So instead, we use toluene, which is just methyl benzene. And I think at this point, we've all used toluene in the lab. Other advantage of toluene is it's got a much higher boiling point than benzene. Benzene boils at 60 something in the 60s. I think it's 60s, 66. No, that's THF. Anyway, in the 60s, and toluene boils at 110. And so another advantage, aside from being less carcinogenic, is you can heat a reaction in toluene a lot hotter than you can in benzene. So I don't know why they didn't just use it to begin with, but because toluene is also found in crude oil. The reason it's the molecule of the day for today is because benzene has a very important resonance structure, and we're going to I'll draw it in a little bit here. Okay, so what I think we've seen resonance structures at least a little bit maybe in Gen Chem, but if not, let's talk about why we need them. So for some molecules, just a single skeletal structure doesn't really do a good job of telling us what the molecule actually looks like. And that might kind of seem counterintuitive because we've spent like the entire semester so far talking about how to draw the molecules correctly. And so now I'm telling you that just kidding, they're not actually correct. Well, they are in some cases. So let's take this molecule, for example. This is an alkene. And what the two lines, right, are telling us is that in between the two carbons, the two sort of carbons in the middle, we have two sigma electrons that are forming the sigma bond or the first bond. And then we have two pi electrons, and those are forming the pi bond or the double part of the double bond. And so what the skeletal structure here is telling us is that those electrons are sitting between the carbons, right? That's we draw the bonds in between the carbons. So duh, that's where the electrons are. The problem is that some molecules don't cooperate so well with this rule. That should say adequate. Okay, because that structure is adequate for that alkene. So what about this molecule? So this is called the allyl cation. And it's got a double bond like an alkene. And then it's got a positive charge on one of the carbons that's next to one of the alkene carbons. If we do spectroscopy of various kinds on this molecule, we will find that all three of the carbons are sp2 hybridized. So we would expect that for the center carbon, because it's got a double bond, and the carbon on the left, it's also got a pi bond to it. But the carbon on the right, at least at this point, it may not immediately be clear to you whether it should be what the hybridization is. But we know from experimentation that they're all sp2 hybridized. And so we'll take sp2 hybridized to mean has pi bonds, or at least one pi bond. Okay. So that is counterintuitive to our drawing because the carbon on the right does not have any pi bonds in our drawing, but we've been told that all three of the carbons have pi. Huh? How does this work? We have three carbons. The pi bond can only go between two carbons, right? Shorter answer is actually no. What we would really like to do is have the pi bond spread out among all three of the carbons. There is a way we can draw that. We'll talk about that in a second. But based on our sort of our normal skeletal structure rules, we can't really do that. We can't draw a traditional structure that has that one pi bond spread over the three carbons. That doesn't really make sense. And additionally, what that means is we're going to have the positive charge also spread among multiple carbons. We'll get to that in a moment. So the way we do that is with resonance structures. And we're going to sort of take a mental average of these two different structures, and that's going to give us the actual structure of the molecule. So the first thing that we drew is a valid resonance structure for this molecule. There's another one though, and it looks like this, right? So two molecules. Now, in this case, they look like they're just flipped. And in this particular case, it's true that yes, these two molecules are identical, but we're going to pretend that that this carbon on the left, that's the other line, this carbon on the right is the same as this carbon on the right? We haven't flipped the molecule. There's something it looks like something has happened to it. Okay, so I've drawn two new different kinds of symbols here. Not really new, but in the middle is a resonance arrow, and it's this double-headed arrow. Okay, it's not a reaction arrow like that. And it's also not an equilibrium arrow, which we usually draw like that. It's unique. So I don't know about you, but when I was in general chemistry and we learned how to draw equilibrium arrows, I didn't like doing this like half arrows thing. For some reason, I thought it looked ugly. And I started to draw this. And I got corrected and I was like, dude, what does it matter? And it matters because there's another kind of arrow. That particular arrow, sort of a traditional double-ended arrow, is for resonance. Okay, and then we also have the brackets, and these tell us that both of the structures represent one entity. Okay, this is important and sometimes a little counterintuitive, I think, for some people. Because the resonance arrow looks a lot like an equilibrium arrow, it's easy to trick yourself into thinking that the molecule is flipping back and forth between those two states. Okay, that is not what's happening. And one thing that I often see students say is, okay, well, it's called a resonance structure, so isn't the molecule resonating between two forms? It's really inconvenient that that's the word that has been chosen for this sort of concept, but here we are. And so the molecule is not resonating or flipping back and forth between two structures. These are two incorrect structures that together show the correct structure. Okay, I think that'll be more clear when I draw the actual structure. And we call that a resonance hybrid. Of course, a hybrid because it's a hybrid of the multiple incorrect kind of structures that we draw. And for the allyl cation, it looks like that. So generally, I'm not going to have you draw the resonance hybrids. I'm just going to get you to draw resonance structures, and we'll do a ton of practice with that. But I want you to see that when we're drawing resonance structures and we're looking at the different placement of pi electrons in a molecule, there's some significant vagueness as to where the bonds actually are. So you can see the sigma bonds, those are drawn explicitly. And then we've got this dotted line that's kind of going all the way across the molecule. That's showing those two pi electrons. Although one dotted line doesn't necessarily mean two pi electrons. It can be all sorts of different numbers of electrons. Again, it's really vague. And then the positive charge I've drawn kind of just in the middle of everywhere. Again, being very intentionally vague here. So in the structure, the pi electrons are split between the three carbon atoms. And this is just what I said, sorry. And the positive charge is really over the entire ion. So we call these electrons delocalized. Really, the pi electrons are delocalized because they're just, well, they're not located in one specific place. They could be located in a variety of different places. So we say they're delocalized. Kind of a funny way to talk about it, but that's the term that we use. Okay. So I've drawn this molecule with two resonance structures, and you might be asking, how do you get from one to the other? What has happened? What atoms have moved? What electrons have moved? And we need some sort of bookkeeping mechanism, pun intended, to keep track of what's going on and to show this, what looks like a chemical reaction, but is not a chemical reaction. And to do that, this is probably the most important part of this particular chapter, is curved arrows. Oh, correction. It might be the most important part of the entire organic chemistry course, but of course not just based on the stuff that we'll talk about today. So this is something we're going to see throughout the entire rest of the organic sequence. And in this particular chapter, we're going to use them as tools for drawing resonance structures and for showing the relationships between them. As I said, we're going to keep using these and keep using these. So they really have two different applications. The first is in chemical reactions, which is really the main use, but not the one that we'll talk about immediately. In chemical reactions, these curved arrows are going to show the movement of electrons. It's kind of like a roadmap is what curved arrows show when we're talking about reactions. But in resonance structures, these are only going to be a bookkeeping device. And we're just basically playing pretend with electrons because, as we know, the resonance hybrid up there is the true structure, and we're not flip-flopping between two different structures. Okay, so a curved arrow, unsurprisingly, is an arrow that's curved. It's got two parts to it. Has a tail and a head. All right. One thing that's particularly important when we end up talking about radical chemistry, so chemistry of one electron, is for now, your arrow should always have a double head and not a single head like that, where it's just got one hook on it. That's a different kind of arrow. Again, there's all the different kinds of arrows, but make sure you have two of the little hooks on the head of your arrow. The tail of the arrow tells us what the source of the electrons is, where the electron's coming from. And the head, unsurprisingly, is showing the destination of the electrons. I know so far this is really conceptual, and I haven't shown you any examples, but we're going to do that pretty soon here. Probably the biggest key to remember with drawing arrows, other than that you're showing the movement of electrons and not the movement of charges or atoms or anything else like that, is that these arrows must be drawn with very high precision. Now, that's a very professory thing to say, I think, but you'll see that this is important because we might have two different parts of the molecule that are very close together, and when you're drawing an arrow from one of those two parts, it's really important that I, as the observer or anybody else, can tell exactly where the arrow is coming from and exactly where the arrow is going to. Okay, so there's only two rules in resonance structures, or RS, for curved arrows. Promise the examples are coming. The first rule is we never make or break a single bond. And so the result of that is that resonance structures have to have the same attachment pattern Ugh. They have to have the same attachment pattern of atoms. Okay. So let's say I have this molecule here with a positive charge. I'm going to draw an arrow that is a bad resonance structure arrow. And then I'm going to draw the result of that arrow, which is correct based on what the arrow is telling me, but does not create a resonance structure. All right. Okay. So again, high precision is important here, even with this wrong arrow. The arrow is starting at this carbon-carbon bond and is ending at this carbon-carbon bond. And the arrow isn't starting at an atom, it's starting at a bond, and it's ending at a bond rather than an atom. There are a couple different places that arrows can start and end. But hopefully I've drawn this precisely enough so that you can see unequivocally that we're starting at that bond and ending at that other bond. There we go. Okay. One of the skills that you'll have to start learning and start practicing is how to interpret the results of a curved arrow. Okay, so curved arrows show the movement of electrons. So this is telling us that the electrons that are making up that carbon-carbon bond are moving over to this carbon-carbon bond. And because there's already a bond here, that's going to give us a double bond here. All right, we're working only in pairs of electrons until we get to radical chemistry. But we're going to move those two electrons from the carbon-carbon bond on the right over to the carbon-carbon bond on the left and make a double bond. There we go. Now, what has that done to our positively charged carbon? Well, now we've given it two more electrons. And now it's happy. So there's no positive charge on that carbon anymore. Another way you could prove that to yourself is by going back and looking at the substitution patterns of positively and negatively charged carbons. Okay, that carbon on the positively charged carbon on the left has three total bonds to it. One bond to carbon, one bond to carbon, one bond to hydrogen. And then here at the end, one bond to carbon, a double bond, so that counts as two bonds to this other carbon, and a total of four, including the hydrogen. So that carbon with the explicit hydrogen on it is now happy and not charged anymore. But that's not all of the atoms that we started with. We still have this carbon and this carbon. So this bond has been broken, gone over there. So this carbon and this, so there's a two carbon chain left over. So we have two products here. And I should use color instead of pointing, I'm sorry. And this carbon here originally had two hydrogens on it. Still has two hydrogens on it, but now one of its four bonds has been broken. So it is now electron deficient. And so it gets a positive charge. Okay, so I said that this was a bad arrow. And the reason it's bad is not because it shows an impossible chemical process. It's not impossible. We've just showed the results of it. But it's a bad arrow because we're trying to draw a resonance structure. And I've drawn a resonance arrow here. And I put it in brackets. So resonance structures are always showing the same entity, just in the different sort of forms that make up that entity. And here we've had a chemical reaction happening. So this is not a resonance structure. So this implies that a chemical reaction is happening. So that breaks our first rule: never make or break a single bond. Clearly, we've broken that single bond because we've split the molecule into two parts. Second rule. We can't exceed an octet for second row elements. So second row is carbon, nitrogen, oxygen, etc. However, if we have less than an octet, that's fine. We can have less than an octet. Okay, so let's say we have this molecule. We have a negatively charged oxygen. It's got one bond and 3 lone pairs. And I'll draw another bad arrow. Okay, again, precision, really important here. So the arrow starts at one of the lone pairs. That's a valid place for an arrow to start. And it ends at this carbon-oxygen bond. So that's telling us that one of the lone pairs of electrons on the oxygen is coming down and forming now a double bond between the oxygen and the carbon. But there's a problem with that. And again, here you'll need to draw out some hydrogens in order to see what's wrong here. So I could redraw this structure like super explicitly. Okay, so what I'm saying is to take the electrons, lone pair of electrons from the oxygen and move it down to form a double bond to that carbon. Do we see the problem now? So carbon can only have 4 bonds. And this carbon here already, before the arrow, already has its octet, 2, 4, 6, 8. So by trying to move more electrons from the oxygen to make a bond between the oxygen and the carbon, that would give the carbon 10 electrons, and we can't do that. That exceeds an octet for a second row element. We're not really going to talk about third row elements, although they can break this rule. But never exceed an octet for your atoms. Okay, so this is that would give our carbon 5 bonds. Okay, let me draw a good arrow for the first time. So there, anyone know this molecule? Acetone, our favorite cleaning solvent. Acetone has a very prominent alternate resonance structure from the way that we usually draw it. We can do that by taking the pi bond between the carbon and the oxygen and moving it up to make a lone pair on the oxygen atom. So started the arrow right in the middle of the double bond. Doesn't matter if you use this one or this one. The 2 lines are equivalent. And the electrons are going to move up, and we're pointing the arrow directly at the oxygen atom. So this is going to result in a resonance structure. Why? Because our 2 rules are satisfied. We're not making or breaking a single bond. Okay. We are breaking a bond, but it's the pi bond of a double bond, not a single bond. And we're not exceeding an octet for any second row element. So the best way to see that is to draw the product of that. And so product looks like this. Yep. Okay. So we haven't broken a single bond and we have not exceeded an octet. Let's count. Okay. The carbon here has 6 valence electrons. It has less than an octet. That's okay. The oxygen, well, these electrons were already associated with the oxygen. So the electron, the total number of valence electrons on the oxygen, correction. The octet, the fact that it has an octet does not change. But now it's got 3 lone pairs and 1 single bond, so it has a negative charge. So carbon has 6 valence electrons, and that's okay. As you might have noticed, drawing lone pairs is very important in resonance structures and in actual chemical reaction mechanisms. So make sure you review your chart of the table of how many bonds and lone pairs give you what charge on which atom, carbon, nitrogen, oxygen, fluorine, etc. Now, another thing that I kind of glazed over or glossed over was the formal charges. And this shouldn't really be anything new, because you should know how to do formal charges, how to deter. Seriously? You should know how to do formal charges, but as a reminder, formal charges are always required. If you draw a structure that should have formal charges and you don't put the formal charges, that's wrong, regardless of what kind of structure you're drawing. And well, really, we should do another example, I think. And so let's do this. Predict the results of these curved arrows. One thing you should note is, at least the way I've drawn it, which formal charges are always required. So that means if I draw a structure for you and it doesn't have formal charges, then it does not have any formal charges. This structure is neutral, no charges at all. And so if we're going to draw a resonance structure, which is just a different view of the same entity, then kind of by definition, our other resonance structure has to be neutral. If we end up giving an atom a positive formal charge, that means an atom somewhere else will have to have a negative formal charge in order to cancel itself out and have an overall neutral charge. Okay. So there's kind of 4 easy steps for predicting the results of curved arrows like this. The first thing I recommend that you do is draw all the atoms and all the sigma bonds. Okay, because in resonance structures, we can't make or break sigma bonds. And so that means that all the sigma bonds have to stay the same and all the atoms have to be in the same order, the same connectivity. So I'll just draw atoms and sigma bonds like that. Then we'll draw the pi electrons and lone pairs that don't move. So based on our curved arrows, what pi electrons or lone pairs do we have that aren't involved in arrow pushing? Well, the only one is the lone pair at the top on the oxygen atom. So the lone pair that's on the left of the oxygen atom, again, they're identical, but just for bookkeeping purposes, the one on the left, that one's moving down. So that's doing something. And then pi electrons, well, we've got that pi bond, the carbon-carbon pi bond that's diagonal. Those electrons are moving because they've got an arrow. And so the only thing that's staying put is that lone pair. Okay. So that's not moving. The third step is the big one, and that is we just have to draw the results of the arrows. Now, curved arrows are all about the movement of electrons. They're not about the movement of atoms. And so, well, I mean, we already redrew the structure, so we can see where all the atoms are. But even if you didn't do that in advance, you can always draw the curved arrow structure, the final product. Again, not a chemical reaction, just a resonance structure. But the other structure that you draw can be in the exact same sort of orientation. All we have to do is move electrons. So the lone pair on the left of the oxygen atom, that's coming down, and the arrow is pointing at that carbon-oxygen single bond, and so that's going to make a double bond there. So that's the first arrow taken care of. The second arrow shows the pi electrons from the carbon-carbon pi bond moving, and this is, again, this is one of those subtle precision things that we have to look at. The electrons are moving from where they are right now in the bond to the carbon atom. Okay, so make sure you don't draw something like that. We're just drawing them going back to where they were. So don't do that. And another thing that's also different is, no, not a square. Please don't do that. You could have also drawn that, which would be incorrect, at least well, what I should say is these two arrows are meaning different things. The blue arrow shows the electrons going to the carbon atom. The yellow arrow shows them moving to the other bond on the other side. Again, so you got to be careful. If you're halfway in between on an exam, I'm not going to know what you're talking about. So you have to be very precise here. Okay, so not that one. Okay, so what did I say was happening? Well, the pi electrons are moving onto the carbon atom. Okay, so carbon atom now has a lone pair. So that's the results of our arrows. But then we have to make sure that formal charges are correct. So this is going to be a matter of remembering that little chart. And based on that chart, if oxygen has 3 bonds and 1 lone pair, what kind of charge does it have? Positive. Okay, if carbon has a lone pair, what charge does it have? Negative. Okay, so the overall charge is conserved. We have 1 positive charge and 1 negative charge. Overall, that's neutral. and we've shown the movement of electrons based on the arrows. Another kind of anecdotal thing that will help you sort of see if what you're doing is correct, kind of just based on the general idea of the arrows, right? Electrons are moving southeast, sort of, kind of down and to the right. Electrons are negatively charged. And so, yeah, okay, our negative charge is toward the southeast, where those electrons are kind of flowing. And where the electrons originally came from, the oxygen, is now electron deficient, so it has a positive charge. So that's just kind of a very hand wavy thing that you can do to check and make sure you've assigned those charges correctly is, okay, the place that the electrons are going towards are going to have more electrons, so they're probably going to be more negative. Could also be less positive. So be careful of that as well. So overall neutral, overall neutral. Questions on this so far? So the vast majority of resonance structures follow one of 5 different common patterns. Well, not resonance structures, but the arrows that we use to do the bookkeeping. So for example, these 2 arrows are both a different or 2 different patterns. But if you can remember these, then you'll get pretty close. So you'll be able to recognize what's happening in most any resonance structure. So the first is an allylic lone pair. Okay. First, we have to define what allylic means. And the allylic position is any atom that's attached to a carbon that's part of an alkene or a double bond, carbon-carbon double bond. So this is kind of like our allyl cation at the very beginning of today. Again, the word comes from the same place. Okay. So here's a molecule. It's a 6-membered ring with 2 nitrogens in it. One of them is allylic. One of the lone pairs is allylic. One of them is not. So the one on the top, is that an allylic lone pair or not? Sorry. So this is not allylic because the nitrogen that we're concerned with is not right next to a double bond. So this would have to be a double bonded carbon for that lone pair to be allylic, and that's not in this case. However, here we have a double bond. So these 2 carbons are making up the double bond. And then directly attached to one of these carbons is a nitrogen atom. And so if we have a lone pair on that atom, that's going to be allylic, and we do. That's I shouldn't use blue because blue is my arrow color. Ugh. Grr. See, this is the problem with using arrows to indicate stuff in organic chemistry is they look like mechanism arrows. So now I am going to draw a mechanism arrow. Maybe I should just not do that. There we go. Close enough. Okay, so we have an allylic lone pair. We can draw a resonance structure of this molecule using this allylic system. Okay. So we're going to go from the lone pair to that carbon-nitrogen single bond. And then we're going to go from this pi bond to that carbon atom. Notice that I've drawn so I don't know about you, but the main bond, the one that's connecting here, it kind of looks like it's the sigma bond because it's sort of the foundation, and then this extra one is the pi bond. It really doesn't matter. You can draw it from this side, or you can draw it from this side. Typically draw it from the outside because you got more space. So the result of these arrows, by the way, are two rules: can't break or make sigma bonds. Okay, we're not breaking any sigma bonds, and we're not making any sigma bonds. And we can't give any second row atom more than an octet. We'll check that at the end, but that's also not going to be the case. That's hideous. There we go. It's a little better. Okay, so that lone pair at the top is not involved in resonance. So see, I skipped some steps here. First, draw the atoms in the sigma bonds. Okay, I did that. Second, draw pi electrons and lone pairs that don't move. Okay, we haven't shown an arrow messing with that non-allylic pair in yellow, so those are going to stay put. And everything else, the lone pair on the allylic nitrogen and the pi bond in the carbon-carbon double bond, those are both moving, so that's going to change. Okay, so now we draw the results of the arrows. Well, the lone pair on the nitrogen at the bottom is moving to make a double bond to that carbon. Okay. And then the pi electrons from the old carbon-carbon bond are moving up onto the carbon atom itself. Again, looking at the precision of that arrow there. So we get a lone pair on that carbon. So you could look at your formal charge chart, or you could do the hand waving method and say, okay, the electron's kind of moving northeast here, generally speaking. And so that might make you think that the northeast end might have a negative charge. And yep, carbon with a lone pair, that has a negative charge. Nitrogen with 4 bonds and no lone pairs should make my plus charge vertical, shouldn't I? There we go. So that has a positive charge. Structure at the beginning has no formal charges. It's net neutral. And the resonance structure that we've drawn is also net neutral. It's got 1 positive and 1 negative charge. Okay, so that's an allylic lone pair. For practice, the simplest example of an allylic lone pair is that. So you should be able to do that one as well. Okay, second is also an allylic thing. But rather than an allylic lone pair, we're going to do an allylic carbocation, so a positively charged carbon. Okay, so allylic position is anyone that's directly attached to carbon that's in a carbon-carbon double bond. So here we have a CC double bond. Directly attached to this carbon is another carbon, and that carbon has a positive charge. So this is an allylic carbocation. So our starting structure here has a charge, and that's okay. We just have to make sure that any resonance structures of this that we draw also have a net +1 charge. In this case, they're just going to have one positive charge. One additional trend that you're going to see in really all curved arrow mechanisms is, well, arrows tend to go toward positive charges more than they go toward negative charges because arrows are showing the movement of electrons. Electrons are negative, so they want to go for that positive charge. So we have some pi electrons in that first leftmost double bond, pi bond, and these can move. And essentially, we're just scooting the pi bond over by 1. So first we'll draw all of our atoms and sigma bonds. Then we'll draw everything that hasn't moved. Okay, that would just be that pi bond on the right. I would caution you against saying, oh, we're not doing anything with the positive charge. Shouldn't we move that? Shouldn't we keep that and include that at this point? You should not do that because formal charge is the last step, and turns out the formal charge is gonna move somewhere else. Okay. Next step is to carry out the curved arrows. So we're going to move the pi electrons from that second bond to the first bond. Okay. So pi electrons are now there. And then we need to assign formal charges. If you drew out all of your hydrogen atoms in this structure, that would make it pretty easy to go in and figure out where your positive charge is going to be here. But the cheating way to do it is to say, all right, well, the electrons have moved to the left, so the positive charge is going to move in the opposite direction. It's going to move to the right. Or you could say, all right, this pi bond is scooting over. Okay, so how many bonds do we have going on here? So this carbon, the first carbon at the first top carbon has 3 bonds shown here and 3 bonds shown here, so it's not changing. But this middle carbon right in the middle, this previously had 3 indicated bonds, 3 carbon-carbon bonds, and now it's just got 2. So it's electron deficient. Again, drawing your hydrogens will show you this explicitly. But when this happens, the positive charge moves to the other end of the allylic system. So again, this is very similar to the first example I showed at the very beginning, except it's a longer molecule. Now, and this is fun, we can do it again. Okay, so we can now take, well, we could move either of these pi bonds. If we moved this one over here, well, we're just going to go back to where we started. But what about the other pi bond? We can move that one as well. So let's move this pi bond here. Okay, pi bond is moving, the electrons are moving toward a positive charge. That's usually a good sign. Okay, just repeat the process again. Draw out atoms and sigma bonds. Then draw all of the pi electrons and lone pairs that don't move. It's going to be the pi bond on the left. Then carry out the instructions. So move those pi electrons from the double bond on the right to this position. And then calculate formal charges, which again, you can do by counting hydrogens or just the fact that the positive charge moves right there because it's lost a carbon-carbon. So resonance structures do not have to be in pairs. They're not enantiomers. And so you could have almost an infinite number of different resonance structures for one particular molecule. Again, we're not going back and forth between these three structures. These are all contributors to one resonance hybrid, which if you like, and I'm not going to require you to draw them, but it might look something like that, right? All of the carbon-carbon bonds, 1, 2, 3, 4, 5, they all at some point are a double bond. And at least one of the resonance structures, usually two, they're a double bond. Okay, so those delocalized pi electrons can go across the whole thing. And then in each different structure, there's a positive charge somewhere in the molecule. And so we just kind of slap it on there somewhere and call it a day. Most chemists wouldn't draw it like this. They would draw whichever resonance structure best suits their agenda. In other words, which resonance structure explains the reaction that they're trying to do. Okay, that's 2 out of 5. Any questions on that one? Okay, cool. Next time we'll pick up with the last 3 and then talk about picking which one of these is more important, because there's an answer to that.